It's Sunday and Josh invited the guys to watch the game at his house. But it turns out that he pulled a fast one, and we have to help him move the couch in order to watch the game. Josh thinks it's easy, but there's a lot that goes into moving a couch. First, we're going to start with deriving the velocity formula. Everyone knows distance is equal to the rate multiplied by the time. So now let's take the derivative of this equation with respect to time. dx dt equals the velocity, and dv dt equals the acceleration. The final velocity is equal to the initial velocity plus the acceleration multiplied by the time. We end up with the velocity formula, equals the initial velocity plus the acceleration multiplied by the time. The velocity is equal to the change in position over the change in time, and by manipulating that equation, we end up with the velocity times the change in time is equal to the change in position. We're going to integrate the left side of this equation from 0 to any time t, and we're going to integrate the right side of this equation from the initial position to the final position. Since we just derived the velocity, we can plug it into this new equation. We now break the left side of this equation into two separate integrals, and then pull the constants out in front. We then integrate the equation and evaluate the limits, and by manipulating the result, we end up with the position equation. So how much work is being done by pushing this couch across the parking lot? To determine that, we first have to find the acceleration by using the position equation that we derived earlier. It took us 4 seconds to push the couch 10 feet. We set the initial position as 0, and since the couch was at rest, the initial velocity was also 0. By plugging in what we know and solving for a, we find out the acceleration is equal to 1.25 feet per second squared to the right. Thanks to Sir Isaac Newton, we know that the force is equal to the mass times the acceleration. Our couch weighs 100 pounds, and by dividing it by gravity, we find the mass of the couch to be 3.125 slugs, which is a unit of mass you've probably never heard of, but we use it because it lets us keep the rest of our measurements in pounds. The force required to push the couch horizontally is 3.91 pounds to the right. This diagram demonstrates how a force can be broken up into its x and y components. The horizontal force is equal to the total force multiplied by the cosine of the angle of the force. We measured our angle of force to be 30 degrees, and our horizontal force is 3.91 pounds. By rewriting the equation and using our advanced knowledge of trigonometry, we find the applied force to be 4.51 pounds, 30 degrees up from the left. Using the applied force, we can now solve for the vertical force. Work is equal to the magnitude of the force vector dotted with the distance vector. From previous calculations, we know the force vector is equal to 3.91, 2.26, and the distance vector is equal to 10, 0. By dotting those two vectors, we find the work done equal to 39.1 foot-pounds. How much is each of them carrying? In this situation, the couch is in equilibrium. When a system is in equilibrium, the summation of its forces are equal to 0. In our system, there are no horizontal forces acting on the couch. In the vertical direction, two people are applying an upward force, and the weight of the couch is applying a downward force. We're trying to find the force that each person is exerting on the couch. Because there are two variables, we need two equations, but we only have one. This is where torque comes into play. The magnitude of the torque is equal to the magnitude of the force times the magnitude of the position vector sine theta. The summation of the torques is equal to the torque of Boris minus the torque of Jonathan, which is equal to 0. Subbing in what we know, the force of Boris is equal to the force of Jonathan, which is equal to what we will now call the force the force plus the force equals the weight of the couch. 2 times the force equals the weight of the couch. So the force is equal to 1/2 the weight of the couch. So now we know that Jonathan and Boris are each holding 50 pounds. Now that they've lifted the couch off the ground, wouldn't it be nice if Josh lived on the first floor? Unfortunately, he doesn't. So will they still be holding the same amount of weight? How much is each of them carrying? In this situation, the couch is in equilibrium. The summation of the torques are still equal to 0. Let's take another approach to torque. The magnitude of the torque is equal to the cross product between the force vector and the position vector. Subbing in what we know, the cross product of the force vector and the position vector of Boris minus the cross product of the force and position vector of Greg is equal to 0. Let's let the length of the couch equal L, which is equal to 6.5 feet. So let's set up our equation. After crossing the vectors, the result is the force of Boris times 1/2 the length times the sine of 60 degrees minus the force of Greg times 1/2 the length times the sine of 60 degrees is equal to 0. Using substitution and algebra, we solve for the force of Greg. The force of Greg equaled 50 pounds. Therefore, the force of Boris is equal to 50 pounds. As we have just demonstrated, the situation is the same, so they're both carrying the same amount. In our diagram, we are not moving, so the weight of the couch is still evenly distributed. But when you are moving on the stairs, an additional force must be applied parallel to the stairs to allow movement. Being the great mathematicians they are, they not only got the couch into the apartment, but they knew everything that was involved in doing so, and were thus rewarded with watching the game. And Josh, who didn't know these things, had to stand.
Hey, you guys, come out!
Far away.
I'm filming it.
Alright. Oh, I'm so glad you guys are here. Hey guys, thanks for coming over for the game. Bad news though, I just ran over your dog. Is there a couch over there?
Should I? The couch is not.
Follow my hand. No, you gotta stay on it.
Oh, yeah. You didn't tell me what.
Don't get the other couch behind them.
Oh, it's already in there. Oh, why not? It's right there.